So welcome to the tutorial, and thank you for coming. I'm Mark Braverman, and today we'll talk about communication information complexity. So before we start, all three of us are from the computer science background, so there is some language difference. We tried to mitigate some of it, but please stop me and ask questions. That's the point of having a tutorial. So communication complexity is a view from the computer science side. So it was introduced within computer science a while ago, over almost 40 years ago, by Andy Yao. And it's actually one of the few tools we have to obtain tight bounds on very different problems. And I'll give a couple of examples. And interestingly, information theoretic connections, even though it's a communication, the problems discussed by communication complexity are communication problems. Information theory connections only came around in the last just over a decade or so. And tight connections are even more recent. And exploring those connections and where we are going forward is actually the point of this tutorial. OK, so the basic communication complexity setup we'll deal with is, so here is an example. We have two parties. They're usually called, so those are terminals, if you will, but it's more fun when they're people. So this is Alice and this is Bob. And each of them has an input. So the running examples in this tutorial, Alice and Bob each has a list of elements from the set 1 through n. So a list of numbers. But Alice is in Hong Kong and Bob is in New York. And they want to answer some questions that depend on both of their inputs. So one example is the equality question. So imagine they have two files of length n, and they want to decide whether those files are identical to each other or not. So that's the equality problem. Another kind of common problems is the disjointness problem, where they want to decide whether they have an element in common. So notice that in both of these cases, the output is just a single bit. So the answer is just yes or no. But so the question is, and they do it by sending messages to each other. So, and the basic question is, how many bits do you need to exchange to solve these problems? OK, so this is the basic setup. So for the equality function, if you are not allowed to make any mistakes, then it's a pretty easy combinatorial proof to show that you actually will have to exchange n+1 bits. So with n+1 bits, it's actually very anticlimactic, the protocol. Alice can just send her input to Bob, and Bob can compute the answer and return it to Alice. So any function actually can be solved with any 1-bit function can be solved with n+1 bits of communication. If you allow a small error, then you can get away with a lot less communication. Indeed, if you actually had to compare two files in practice, you would never send the entire file. You would just hash it and compare the hashes. And if you send just k bits of hash, your probability of a collision and of a mistake is 2 to the minus k. So if you allow an error epsilon, you get away with log 1 over epsilon bits, which potentially is a lot less than n. On the other, OK, so that was the equality example. Now for the disjointness example, again, without errors, it's again not hard to see that you need the same n+1 bits. It's again a fairly straightforward combinatorial proof. The question is, OK, so now the question is, if I allow you a small error, say error 1 over n. So remember that with error 1 over n equality, you could do in log n bits. Can you do better than linear? Can you solve this problem with little o of n communication? So do something that's qualitatively better than just send your input, exchange your inputs. Or turns out the answer to this question is no. And OK, so in case actually, but you can do better than n. And that will be one of the upshots of this tutorial. So in case you're bored or lost or at some part of the tutorial, here is a specific exercise. Try to solve it in 0.7 n. And for extra credit, so the next part is cruel, but try do 0.5 n. It's still possible. But so that's an exercise. OK, so that was the prologue introducing communication complexity. So why do we care? Actually, most of the applications of communication complexity is not to actually solve communication problems, but to prove lower bounds on computation. So unlike communication theory, if you look at the theory of computational complexity, it mostly consists of open problems and conditional results. So most of the really things that we would like to know, like P versus NP, are hopelessly open at this point. So unconditional bounds about general computation are pretty far out there. But we can often obtain tight bounds for restricted models of computation. So if we somehow restrict the ways in which you can interact with your inputs, then we can actually get tight bounds to various interesting models of computation. So I'll give two examples in more detail just to motivate this area. But there are many more. So basically, streaming I'll mention, data structures, distributed computing, which that one seems pretty natural, VLSI design, circuit complexity, and there are many more other examples. So let me just give you two examples in more detail. How can, basically, the way all of these examples proceed is you introduce a model of computation, and then you say, if you could do really well in this model of computation, you could get a too good to be true communication protocol. And then you use communication lower bounds to prove lower bounds on this model of computation. And often you can get tight bounds, actually, on the model. So in the case of streaming algorithms, so we have say a router here. So it's a processor that has an access to a very long stream of data. So X is the input, but X has n bits of data, and n is way bigger than what you can store on your processor. So in your processor, you only have S, which is much less than n bits of memory. So think about, so a router is actually a good example. So you have 10 to the 15 bits flowing through it, but only 10 to the 9 memory, say. So you want to compute some function of the stream. So examples are approximate number of distinct elements, frequency moments, which is another type of statistics on frequencies of the elements, and so on. So how can you connect this to communication? So here is the trick. In this case, it's a pretty straightforward trick. You take your input, and you just partition it into two parts. Let's call them XA and XB. They're just two parts of the input, the first half and the second half. And you define a two-variable function, f of XA, XB, as just f of the combined string. Now you give the first half to Alice, the second half to Bob. If there is a good streaming algorithm, how many bits do Alice and Bob need to exchange in order to solve f? In order to compute f of x1 and x2. Just S, right? So Alice will do the first part by herself. She doesn't need to communicate at all. Then here she needs to pass the baton to Bob. She'll just send the contents of the memory to Bob, and Bob will continue from there on. So this means that you get, if you have a memory S streaming algorithm, you get a one-message protocol that uses S bits of communication to compute F. And the way you would apply this is if you have a communication lower bound, so if you prove that your function requires a lot of communication, then it means that you cannot have a streaming algorithm. You need the same, for example, for many problems, you can actually prove that you need a linear amount of memory. And multi-round communication with the same reduction essentially corresponds to multi-pass streaming. So if you had an algorithm that passes 7 times over the data, that gives you a 14-round protocol that uses 14 times S communication, because they would need to switch contexts 14 times. So that's one example. A second example is for VLSI design. So this is a very simple model, but basically, so there is a function. So any questions? So there is a function, f of the input x1 through xn, and we want to lay out a circuit on the grid that computes f. And the goal is to establish trade-offs between the area of a circuit and the time, the number of clocks it takes to compute f. So the goal would be to show that either you need a very large circuit or it will take many clocks to compute it. And this type of bounds relies exclusively on communication complexities. So how would we do it? So we have the circuit. If it has area A, then it's possible to find a cut in the circuit that cuts the inputs in half and has only root A surface area. So essentially, if the circuit is rectangular, cut it along the shorter edge. If it has a fancier shape, then it requires a little more effort. But basically, you can find a cut that's root A that only cuts root A wires at most. Now give the left side of the brain of the circuit to Alice, the right side to Bob. So suppose we have T rounds of computation. How much communication do they need in order to execute this computation? So each of the T rounds, to execute it, they only need to exchange at most root A bits, because Alice will give Bob the wires that go from left to right. Bob will give Alice the wires that go from right to left. So a computation, if you have a circuit with these parameters, you get T rounds of communication with root A communication each. And therefore, the communication complexity of F with this partition is at most T root A. And this gives you a trade-off. So, I mean, the way I proved it to you, I gave an upper bound of communication, but the way it's used is you start with a function that has high communication complexity, and this implies a trade-off, a lower bound on time times area. So, so those are two motivating examples. So the main takeaway message is that the hardest and most interesting part for communication complexity is actually the lower bounds part. And those get actually pretty tricky. Over the years, many lower bound techniques have been developed and are being developed. It's a very active research area still. Early techniques were combinatorial in nature. So one general approach is to look at the truth table of F. So you represent it as a matrix and study properties of this matrix. And information theoretic techniques are more recent. And actually, those connections, they give rise to some fundamental open problems that are I think, of independent interest. So we'll actually, since it's an information theory conference, we'll talk a lot about those later in the tutorial. OK, so let's be a little bit more formal now with respect to the model. So that we'll focus on the two-terminal, two-party communication complexity. So the goal is to implement some function f of xy. And the tool that's being used is a communication protocol, which can be thought of as an interactive code book. So basically, for this talk, we'll assume that Alice and Bob have an access to a shared random string. A lot of the time, this assumption doesn't matter, but it just simplifies things. And they also have access to private randomness. But notice that at least for communication, we can, without loss of generality, we can assume that all the randomness is public. Because if they need private randomness, they can just designate part of the shared randomness to be private. And a communication protocol is just a sequence of functions that tell each party what to say. So the first message depends on the input and on the randomness. The second message and each subsequent message depends on the input of the party who is speaking and the randomness and the conversation so far. So formally, this is what a communication protocol is. It's a series of functions that depend on the past, on the input, and on the randomness. And the communication cost of a protocol is the number of bits exchanged during the execution of the protocol. So in the distributional setting, we assume that there is some distribution mu on the inputs to the function. So x and y, the inputs are distributed according to some mu. And the communication complexity, if you have, with error epsilon, is the communication cost of the shortest protocol that actually manages to solve f with error at most epsilon. So it's the minimum over all protocols that do what they're supposed to do. So they output the correct answer with probability at least 1 minus epsilon, and you minimize the communication cost. So for example, in the equality case, the answer with error epsilon was log 1 over epsilon. It's also, OK, so in many cases, we do not want to assume a prior distribution on the inputs. So here, notice that here, the error is measured with respect to mu, but we are allowed to be completely wrong on some inputs. So sometimes we don't want, actually, to assume a prior distribution on inputs. And instead, it's also possible to talk about randomized communication complexity. And in that case, the specification is that there should be an error of at most epsilon on all inputs. So which definition is more restrictive, actually? So which one is harder? The second one is harder, right? So because if you are right with probability 1 over epsilon each input, you're also right with probability 1 minus epsilon, actually with respect to all distributions simultaneously. But it turns out that it's not a big restriction because of the following theorem, which follows from a minimax argument, that there is, for each problem and for each error, there is the worst distribution. So there is a distribution such that computing f with respect to that distribution is as hard as computing it correctly on all inputs. And the way you prove this theorem is using a minimax argument. So basically, there are two players. One is trying to come up with a hard distribution. One is trying to come up with a good protocol. And the minimax theorem allows you to switch the quantifiers. So if for each protocol, for each distribution there is a good protocol, then there is a protocol that works for each distribution, which particularly means that it works for the singletons. Yeah?
It's a question regarding the model from last
Mm-hmm.
time. The players, they alternate, or does it matter? It's all exchanged.
So here, the messages can have more than one bit. So then you can assume that they alternate without loss of. So generally, no, we don't need to assume. We don't assume that they alternate bit by bit. In many cases, if you don't care up to a factor of 2, it really doesn't matter. But actually, sometimes alternations is a resource we care about. So remember, in the streaming model, for example, it would be useful to use the fact that we only send one alternation or a few alternations. But yeah, so that's, in general, the M's can have many bits. OK. OK, so as I mentioned, in this language, the communication complexity of equality is log 1 over epsilon for all mu's. And it's actually a theorem that, one of the classical theorems in communication complexity is that there is a distribution such that the communication complexity of disjointness is linear. So you need some constant times n communication to solve disjointness. We'll actually find out what the constant is later in the tutorial. OK, so some notes that might be useful based on our experience. So first of all, by default, the problem is a single-shot problem. So there is no, so we will sometimes talk about a stream of problems, but by default, there is a single instance of a problem. So Alice gets one input, Bob gets one input, and they need to compute one output. It's not a stream of problems. So still there is a parameter n, but it's the size of a single instance. So the size of the output, for example, in disjointness doesn't grow with the size of the input. The output is still a single bit. Whether n is 1,000 or 1,000,000, the output is still a single bit. And that's the experience with many problems, actually. So we assume that Alice and Bob have access to a shared source of randomness. Actually, in the distributional setting, this is without loss of generality, because you might as well, because if your error is good in expectation over the randomness, you can also find a specific randomness for which the error is good and just fix it. So you can always replace it with the deterministic protocol. OK, so now I want to talk about the broader context of where this thing is going. So this is, in my opinion, I mean, it's a biased view, but so one-way communication theory is it's a classical theory, a beautiful theory. It's very well understood. Information theoretic tools kind of kill it in the sense that pretty much any basic problem you ask, you have a precise answer, and it solves many of transmission problems, at least the basic ones. So two-way communication, in terms of tools, they're still being developed, and unfortunately, it's not as clean as one-way communication. So communication complexity is essentially the field that studies it. And the tools needed are both combinatorial and information theoretic. And we'll actually see some evidence that in as much as we wish, it doesn't look like you can just get rid of the combinatorial tools and only use information theoretic tools. And there are many applications to restricted models of computation. So the next natural step, which is kind of a future, but maybe not sci-fi future, is building this theory for multi-terminal communication. I'll get back to it in the end. So far, the tools there for whatever bounds we have are combinatorial. Actually, it's still an open problem to adapt information theoretic tool to this setting, which is, I think, a very interesting open problem. And the applications would actually be even more exciting computational lower bounds. And finally, general computation, which is kind of getting bounds there, is in the realm of sci-fi for now. So essentially, in terms of tools, the only tool we have is diagonalization, the tool that Turing used to prove that Halting problem is undecidable 80 years ago. That's essentially where we stand. There are a few combinatorial tools for very restricted models, but we need other tools. So one of the major questions is whether we can kind of keep pushing along this direction and import some of the information theoretic tools into the theory of computation. But today, most of the focus will be on the two-terminal communication. And the focus more specifically will be on where information theoretic tools fit into this story. So there are several questions for which information theory appears to work particularly well. So one is understanding, actually, remember I told you that we look only at one instance of a problem. It's still meaningful to ask what happens when you take many instances. How does the cost scale? And for these types of problems, maybe not very surprisingly, information theory has something to say about it. But actually, the answer is not as perfect as you would hope for, but it does give us a lot of mileage. That's one type of questions. Another type of questions is given exact communication bounds. So for example, we know that the communication complexity of disjointness is linear in n. What is the coefficient? So inherently, the tools that are involved in combinatorics are lossy. So you cannot hope to get, or at least it's not. I would be extremely surprised if you got exact bounds with purely combinatorial techniques. Information theory is better equipped to give those answers. So, and also things like understanding the role of interaction and interaction communication trade-offs and so on. So there are many other questions, but we'll focus on the first two. So let's talk about communication complexity under tensorization, so under taking many copies of a problem. So we have a function f with inputs distributed according to x to some distribution mu. Let's denote by f to the k repetition of f. So now I give you, instead of getting one instance xy, you get k independent instances x1, y1 through xk, yk, distributed according to say mu to the k. We want to solve each copy with error epsilon. What is the relationship between the cost of one copy and the cost of k copies? So it's not hard to see that k copies do not cost more than k times one copy, because you can always just run the things independently. But does the converse hold? Is it true that k copies cost as much, up to say a constant, as k times one copy? Or can we sometimes get a volume discount for solving many things in parallel? So in the computer science literature, this is called the direct sum problem for communication complexity. And it's actually, direct sum comes up in computational complexity because it's a tool for making hard problems harder, which is something that sounds bad until you realize you want to actually prove lower bounds. So, you manage to prove some little lower bound and you want to amplify it. And so forcing someone to do many copies of a problem, that is one way to amplify the hardness. But here is a spectacular example where direct sum fails elsewhere in computation. So consider the problem. I take some random matrix A and consider the problem of multiplying A by a vector V. So it can be proved that, so you want to, given a vector V, you want to output A times V, and it's not hard to say that, it's not hard to see that just because of the size of the input, you need n square communication, n square steps of computation to solve this problem, to multiply an n by n matrix by a vector. So how much does it cost to multiply A by n different vectors? Well, sure, we can run the thing n times, so we could do n cubed. Can we do better? Well, OK, so it's a very contrived way to present what problem? Matrix multiplication, right? So I can arrange those as columns of a matrix, and so we get a matrix A by V, and we can do it in n to the omega, which is so significantly better than n cubed. And notice that this is, it's not, unfortunately, this doesn't happen for some stupid reason. Like, it's not like a concentration phenomenon or anything like that. It's because there is an interesting structure that you can exploit and do matrix multiplication better. And we still don't know what's the best. For all we know, it could be n squared up to lower order terms. OK, so that's just a cautionary tale saying that if you remember this big table, so if you go all the way to the realm of computation, direct sums will start failing. So we can't take it for granted. OK, now let's look at the other extreme. Let's look at the transmission case. How does tensorization behave there? So just for simplicity, let's look at a very concrete problem. We want to be transmitting treats. So T is a uniformly distributed treat. And we want to transmit it using a prefix-free code. So it's an easy exercise to see that you need to transmit a single treat, you need 5/3 bits to do. That's the best encoding you can do. Transmitting 2 treats costs 29/9, which is actually, so tensorization fails, but not miserably, not like in the case of matrix multiplication. OK, so, but in this case, so C of T, the communication cost doesn't tensorize, but it's close to tensorizing. And in fact, we know exactly what the correct way of looking at this problem is. Instead of looking at C, let's look at Shannon's entropy. So Shannon's entropy, it's the limit of the transmission cost of T as K goes to infinity. It's log to 3. And it tensorizes because, well, If you define it like this, then it tensorizes just by definition because jumps of 2 cause it to tensorize. But anyway, so that's a simple fact. And by Huffman's coding, actually, it is true that H, it's not only the case that H is better behaved, but also it's very close to C. So by abstracting away, instead of talking about C, by talking about H, we only are off by at most a single bit. And therefore, if we, OK, so the communication cost of k copies of T is bounded from above by k times C of T, and bounded from below by k times C of T minus 1. Because of this side of the inequality. So this is the interesting side of Huffman coding. So this part is the source coding, and this part is the interesting part. OK, so that picture makes one jealous when talking about communication complexity. So we wish things were as simple in the case of interactive communication, but let's see what actually happens. So first of all, it would be useful to have a quantity IC, which is called information complexity of F, which is the interactive analog of Shannon's entropy. So it's the scaling limit of the communication cost of F as k goes to infinity. So this quantity tensorizes for a silly reason. So it's just because as long as it's not hard to prove that the limit exists, and once it exists, if you jump in 2s, then it will be the same limit. So it tensorizes almost by definition. But the question is, does it have a nice description? It turns out that it does. And so let's see what it is. So remember then that when we defined communication complexity, the definition of communication complexity consisted of 2 parts. First, we defined the communication cost of a protocol, which was just the length in bits. It wasn't very impressive, but it was a definition. And then the communication complexity of a problem was the smallest number, or the cost of the cheapest protocol that gets the job done. So here again, we need to define, before we can talk about information complexity, we need to define the information cost of a protocol. So here we are back to this diagram from before, and we let capital Pi be the random variable representing the transcript of the protocol. So here is the protocol, and here, for a reason I'll explain in a second, it's actually important to have private randomness. So this is the formula for the information cost of the protocol. It's, in words, this is what Alice and Bob learn about each other's inputs from the conversation. So what do Alice and Bob learn from the conversation about each other's inputs? So this term, for example, is what Alice learns from Pi. It's the mutual information between the transcript and Y, given the things that Alice has access to, which is her randomness, public randomness, and X. And similarly, this is what Bob learns. So again, in words, the information cost of a protocol is how much do the parties learn about each other's inputs. So here is a simple example that will help us to get used to the definition, but also will show us why shared randomness matters. Private randomness matters. So consider the following protocol. Alice takes her private randomness, assuming there are enough bits, does a bitwise XOR with X, and sends it to Bob. So that's my entire protocol. What is the information cost of this protocol? So how much well, Alice learned nothing because she only speaks, she doesn't listen. What does Bob learn about X? Nothing. So the information cost of Pi is 0, regardless of what the prior is. Now suppose I got rid of the private randomness or made it public. Suddenly, you learn everything. So the information cost is actually the relative entropy, which is all the information available in X to someone who already knows Y. So private randomness actually matters a lot, and we'll see this in other examples. So here's just an example to get used to the notation and to the notion. So say we are trying to, remember, we are trying to solve the equality function again. And the prior distribution is such that with probability half x is equal to y, and with probability half x and y are just drawn uniformly at random from some huge alphabet. And the protocol is the following. Alice sends an MD5 hash of x to Bob, and Bob compares it to his hash and responds with an answer. So the probability of this protocol being correct is roughly, or being wrong is roughly 2 to the minus 129, because you're wrong if the x and y are different, but the hashes collide. It's a very rare event. What is the information cost of the protocol? OK, so the easy part first. How much did Alice learn from this conversation? How many bits, roughly? 1 bit. Why? Well, because she roughly learns the answer, whether x is equal to y or not, and her prior was roughly uniform, so roughly 1 bit. Now the hard question, how much did Bob learn from this interaction? So it's a number between 0 and 128. So any ideas? Hmm? Yeah, it's a public function. Everyone knows it. Yeah, otherwise he wouldn't be able to do this part. So, OK, so you would think it's something like 128 because he learns the hash. But it's actually not. It's roughly half of it. Why? Because half the time he actually learns. So if they're different, he learns something interesting about x. He learns the hash. If they're equal, he only learns the fact that they're equal. He doesn't learn the hash. He already knows the hash. So then the transmission is only worth 1 bit. And in the other case, it's actually worth 129 bits. It's worth the fact that they're different, and here's the hash. So it's 65 overall. So the answer is 66. So that's the information cost of this protocol. So now, OK, so that was just an example. Now we can define the information complexity of f as just, OK, so in communication complexity, we were trying to solve the problem while minimizing the number of bits exchanged. In information complexity, we try to solve the problem while minimizing what we learn. So we don't care if we communicate for a very long time, as long as we don't learn much. So it's the infimum over all the protocols that get the job done of the information cost of the protocol. And this infimum, so if you notice there's a difference, this infimum is actually needed, because the infimum is not, it actually could happen that the infimum is not attained by any specific protocol, and this already happens with a 2-bit end. So just computing the end of 2 bits, which is a problem we'll dive into in some detail in a little bit, is already requires this infimum here. OK, so another remark is that information complexity, just by definition, is an average case quantity, just like entropy is an average case quantity. Whereas communication complexity is a worst case quantity, even though it is meaningful to talk about average case communication, mainly for historic reasons, people talk about worst case communication. So remember that C of t, the way I phrased it before, actually was average case, the 5/3. So as long as the error is constant because of Markov's inequality, it actually doesn't matter. Also, it is meaningful. It's possible to talk about worst case IC by looking at information divergence and bounding it from above. You can also talk about mean entropy type of quantities, but they're not as nicely behaved. So, but they are important if you want to do various second-order analysis.
Question.
Yeah?
So what is the worst case in the community? You have a fixed distribution, right? So what is
So worst case means that if you have a protocol that sometimes I look at the maximum number of bits exchanged. So even if half the time you exchange very few bits, you still pay for the worst case. Okay, so the fact is that if you define information complexity the way I defined as this infimum, it actually is exactly the same as the scaling limit of communication complexity of many copies. And an important fact that is actually a prerequisite to this theorem is that information complexity tensorizes. And so it's a fact that Rotem will prove later on. And to prove this theorem, one direction is Wiener-Zieff type compression arguments, and the other direction actually is where tensorization is used. So, that's kind of something, that's what gives operational meaning to this quantity. And in fact, there is you can get a remote converse for information complexity. So you can get a stronger statement that says that if you try to solve k copies of f, and you try to use, so we know that in the limit, k copies of f costs this much, k times the information complexity of f. Suppose you are trying to do it with asymptotically less communication, then your chance of success is essentially exponentially small in k. So you get this sharp threshold from the very improbable to very likely. So in terms of success probability. And the proof actually is surprisingly difficult compared to other theorems in this area. So it connects to some deeper things in complexity theory, like parallel repetition, where it still remains to fully understand those connections, but it seems that something is going on there. And just as a pointer, in the CS literature, this is called the direct product. This type of statements are called direct product theorems, as opposed to direct sum. And the reason is you multiply the probabilities. I guess that's why it's a product. OK. So just to recall, remember that we started this conversation because we wanted to understand this question, the direct sum question. Do I get a volume discount when I try to solve many copies of f simultaneously? So is it true that the cost of many copies of f is k times the cost of one copy? Well, this is a question that doesn't talk about information complexity at all, but since we already introduced those, let's write them down. So here downstairs, there is a perfect equality because IC tensorizes, just like Shannon's entropy. This theorem tells us that in the limit, at least when k is large, CC of many copies of f behaves like k times IC. So this is roughly equal. So this question becomes equivalent to this question. Right? So it's just because this part of the diagram collapses, it becomes equivalent to this question, which is a question about the relationship between the information complexity of a single instance of f and its communication complexity. So again, as before, there is the easy direction, which is that the information complexity is at most the communication complexity, because if you exchange b bits, you don't learn, in total, you don't learn more than b bits of information. What can we say in the opposite direction? So in particular, is it true that if IC is low, then CC is low? If you can solve a problem with few bits of information, does it mean that you can solve it with few bits of communication? In other words, it's almost equivalent to asking the following question. If I give you an uninformative protocol, pi, so if I give you a protocol pi that doesn't, in which the parties don't learn a lot, can I is it possible to simulate it by a protocol that exchanges few bits? So Huffman coding does exactly that for the one-way regime, right? So if I have a distribution of messages that are very long, but whose entropy is low, I can re-encode them in a way that essentially pays the entropy plus at most one bit. So if I'm given an uninformative lecture, I can re-encode it as a very short one. But if you're having an uninformative conversation, it's not clear. That's actually the question. Can you re-encode the conversation into one that uses few bits of communication? And that's the IC versus CC problem. So as I mentioned with Huffman's, in one-way regime, it is true up to a +1 factor. So unfortunately, this question, the answer is no. So you cannot compress interactive conversations in general. I mean, I don't know if it's unfortunate or not. It is so. But it means that there is something interesting going on. The proof is via a concrete example. So Rotem will show one version of such an example. And the lower bound proof combines combinatorial and information theoretic techniques. And in some sense, it suggests that you need both because, OK, it's never going to be a precise statement. But in some sense, if you had a purely information theoretic technique, it would also apply to IC, not just to CC. So once you've managed to separate the two, it means that some of your technique has to be combinatorial. And it means that in general, for interaction, we will need both kinds of techniques to fully understand interactive communication. So there is still, so this problem is still not completely, pretty far from being settled. So we'll see more about it later in the tutorial. But let me move on to specific applications to exact lower bounds in communication complexity. And specifically, we'll talk about the communication complexity of set disjointness. Yeah?
So just like communication complexity has applications in streaming and other problems. Knowing information complexity bounds, is there like a natural use for this?
So this will be one. The one I'll just show now is one example. So for exact bounds, in general, it actually, many of the techniques that previously were designed for communication also apply to information. So you immediately get a stronger statement because an information lower bound is logically stronger than a communication lower bound. And you can get some mileage of it in several settings. Quantum is one example. But let me let's talk about disjointness. So remember, the disjointness question is Alice and Bob get subsets of 1 through n, so lists of numbers between 1 and n, and they want to know, is there an element in common? And let's say the error is small. It doesn't matter what it is as long as it's not too small. Let's say it's 1 over n. So it goes to 0, but not too fast, not exponentially fast. So it's a classical result that the communication complexity of disjointness is linear. And you can actually, just by using this result, this implies that it scales as some constant times n plus little of n. What is this constant? OK, so to answer this, we need to take a closer look at the disjointness function. So instead of looking at x and y as sets, let's represent them as vectors. So xi is 1 if I is in the set, and xi is 0 if I is not in the set. So the sets are not disjoint if there is an entry where xi and yi are both 1. Right? That means that I is in both sets, so they're not disjoint. So disjointness is just an OR of n's. So it's made from n copies of the 2-bit end. And why is this good news? Because information complexity is about understanding communications of many copies of a problem. So essentially, it's solving n copies of the 2-bit end. It's not quite that, because for hard instances for disjointness, we have xi and yi is 0 on almost all the coordinates. Because if I have an input where for many coordinates the xi and yi is not 0, I can just subsample the input and solve disjointness very easily. So if my intersection is n over 10, then with like 20 bits of communication, I can find one of the places with good probability. So in hard instances, the xi and the yi is 0 on almost all coordinates. And what it translates to is solving a bunch of n's on prior distributions where there is very little weight on the 1, 1 entry. And with some work, you get this exact statement. So the constant for the disjointness function, because there are n copies of them, so the constant for the disjointness function is the information complexity of n taken on priors where there is no mass on the 1, 1 entry, or very little mass. But you can take it to 0 as n goes to infinity. So essentially, you get an exact expression for this constant, and all that remains is to compute the information complexity of n. And yeah, so that's what remains. So in case you were lost in the previous analysis, now it's a good place to reconvene. Here is a very concrete problem. Alice and Bob each get a bit, so it's 0 or 1. They want to compute the end of the 2 bits. They want to know whether both bits are 1 or not. And they want to reveal as little information as possible to each other about their bits. So the answer for any mu is a number between 0 and 2. It's non-negative. And at worst, it's 2. Even if you just exchange your inputs, which is the most naive thing you can do, you never reveal more than 2 bits of information. So it's a number between 0 and 2. And so what can we do? So here is a naive protocol for AND. Alice sends X to Bob, and Bob computes X and Y and returns it to Alice. So what's the problem with this protocol? Well, if you have a 1, if Bob has a 1, for example, he will learn X no matter what, because X is already encoded in the answer. But what is the bad case in some sense? I mean, it won't be a precise statement, but what's wrong with this protocol? If y is 0 and say x is 1, Bob has no business knowing that x is 1. Somehow it's a waste. He shouldn't have learned this. Maybe if we were more clever, Bob could reveal that he has a 0 without learning too much about Alice. And so indeed, so that's not an optimal protocol because too much is revealed if x is 1. So here is the optimal protocol. It's for the special case where the prior distribution is symmetric, so the probability of 1, 0 is equal to 0, 1. If it's not symmetric, then an extra step is needed. But let's just stay with this case. So here is the protocol. It actually relies on using private randomness, and that's necessary. So Alice looks at her input. If it's 1, she sets her number A to be 1. A is just some number between 0 and 1. If x is 0, she picks her uniformly random number between 0 and 1. And Bob does the same. So they both now have a number. So Alice has a number A and Bob has a number B. And now there is a public clock that goes from 0 to 1. They locate, so there is an interval 0, 1. And the clock goes from 0 to 1. And when your number is called, you raise your hand. OK? So that's the protocol. So why is it correct? What happens if someone raises their hand before time 1? They reveal that they have a 0, and the protocol stops. If the protocol reaches 1, that means that both have 1, and that's 1. So OK, a hand-wavy explanation. Why is it good? Well, because it seems to at least partially solve the problem we had before. So say Alice raised her. So someone will have to raise their hand, because to be correct, you need to learn to kind of be sure that the end is 0. You need to publicly acknowledge one of the parties to have a 0. So someone will have to raise their hand. But at this point, Alice raised her hand. Say she had 0.5. She has uncertainty about what Bob has. So she's kind of more biased to believe that Bob has a 1, but she didn't learn that Bob has a 1. She learned, so she's more biased, but she doesn't know whether Bob has a 1, or maybe Bob has a 0, but he was just by luck, he got B to be equal 0.8. And it turns out that this protocol reveals as little information as possible for the end function. So how do you actually prove this effect like this? So the strategy is actually, it turns out that while proving optimality for one distribution, you might as well look at all distributions simultaneously. So,
Question.
yeah?
So before the protocol, so I'm having trouble understanding the timing and the messages.
Yeah, it's deliberately confusing. And okay, so why? Because remember I promised to you that the infimum is necessary. So that means that I can't give you a protocol, actually. So this is a limit of a protocol. So you could discretize the time. And for each discretization, you would get a protocol. And in the limit, it will converge to the right thing. So that's a good catch. Yeah, so this is not a real protocol.
So once you discretize, you just send empty messages till the time.
Yeah, exactly. And actually, so I'll return to this point. But yeah, that's a good catch. And it's essential because there isn't a single protocol that the number of messages has to go to infinity as your information cost converges to the information complexity. So how do you prove that this protocol is optimal? Well, let's denote by psi the information cost of this protocol. So we guessed what the information cost is. How do we prove that it is the right cost? Essentially, it's an inductive proof. So we need to verify two things. That this function is 0 when no further communication is needed. So for example, when we are sure that both parties have a 1, the information that this function has the remaining cost is 0. And the second condition is it's a bunch of concavity-like conditions on the cost as the protocol progresses. So essentially, it corresponds to the inductive step argument when you actually prove it. So let me give you just one step of the induction. So if you have this type of condition, so if you have an R-step if you manage to prove that for all R-step protocols, the information cost of this protocol is at least psi, then because of this invariant, it also implies the same statement for R+1 step protocols. So it's just some type of condition that allows you to maintain it. It's actually easier. Once I tell you that such a condition exists, it's easier for you to reconstruct it than for us to go over it on the slides. But basically, there are conditions like this. You verify all of them, or students verify them. And you prove that the protocol is optimal. So as been mentioned here, this is not a protocol. It's actually a family of protocols you get by discretizing time. And we can actually estimate the slug caused by discretization. It's on the order of 1/r². So it means that if you insist on a bounded round protocol, you'll actually end up paying a constant overhead in terms of information. And now we can reveal what this alpha constant is. Just we have the entire function, we can maximize it, and you get this as your answer. So it's just over half. So it was a pretty cruel exercise. So we can solve disjointness using this times n communication, but the protocol is not very explicit. The best description I have for it is take the rising counter protocol, fix some big R. So if you want this, you need R to be like 20 or 30. And then use something like Wiener-Zipf to compress it round by round. So it's not very if you remember what disjointness looks like combinatorially, it's not a very natural protocol, but actually it's probably the optimum. Okay, so you can actually use this template to more generally, it's just to give a comment that things that are we can take for granted in one-way communication are highly non-trivial. Actually, just computing the information complexity of a function from its truth table is a pretty painful exercise. So for R rounds, it's a little easier, but for unrestricted general functions, it's actually it looks like it should be easy, but it's actually it's not that. It's pretty painful. Okay, so let's talk briefly about some open directions. So the first open direction, which we talked a little bit about, is better understanding the relationship between information and communication. And another way to phrase it is understanding the limits of interactive compression. So how big of a gap can you have between a conversation that's uninformative and how short you can actually make it in terms of compressing? And that will be, so here there's been some progress, so we'll talk more about it later in the tutorial. A second direction that is actually kind of more open-ended is building a credible theory of information complexity for 3 or more terminals. So once you're above 2 terminals, all the techniques we have are actually combinatorial, so methods involving tensors and so on. And the third direction is that I'll talk briefly about is interactive coding theory. So remember in this picture, so I'll talk about multi-terminal information complexity first. So where it fits in this picture is moving from the two-way to the multi-terminal communication, and in particular seeing whether information theoretic techniques can be fit in there. So let's see what goes wrong actually. So you could still try to naively extend the definitions from before to Alice, Bob, and Charlie. So we have Alice, Bob, and Charlie, and they try to learn as little as possible about each other's inputs while computing some function of all the inputs. So where we run into trouble is the role of private randomness. So remember in the two-party setting, in the two-terminal setting, we had 2 types of randomness. We had public randomness and private randomness. How many types of randomness are there in this 3-party setting? Yeah, there are unfortunately 7. So there are also semi-private randomnesses that are shared by 2 of the 3 parties. And the question is, do you allow or do you not allow that type of randomness? So if you allow 2-terminal randomness, that's equivalent to allowing private channels between every 2 parties. Because every time Alice wants to send a private message to Bob, she can XOR her message with this private randomness, so Charlie can't read it. And using secure multi-party computation, you can actually show that in that case, you can compute any function without learning anything except for the answer. It's an unfortunate fact about, or a fortunate fact, about, exciting fact, about multi-party computation. So essentially, if you did allow that type of randomness, information complexity would be 0 for all functions. Question? So for communication, it doesn't matter because we may as well make all randomness public. It's actually an interesting duality because for communication, public randomness is better than private randomness, strictly better than private randomness because we can always pretend, just designate part of the public randomness to only belong to Alice and pretend that that's the case. Interestingly, for information complexity, it's the exact opposite. Private randomness is strictly better than public randomness because you can start by taking Alice can start by taking some of her private randomness, sending it to Bob, and now they can use it as public randomness, and that costs us nothing because it reveals nothing about the inputs. It's a free operation. So actually, it's an interesting duality, but the short answer is that for communication, it's enough to only use shared randomness. Okay, and if you don't allow, which it's not clear how to make tensorization work because tensorization, as you'll see in the 2-party case, actually uses, in an essential way, it uses private randomness. And to make a similar proof work for multi-party, you need this semi-private randomness. So, but it's a technical, I think that and something should work. And the real problem is that you could have very complicated correlations between the three inputs. So in the product distribution case, for example, we could do it, but for general distributions, that's the real problem. So finally, let me mention the problems about interactive coding theory. So that might be of actually more interest to this audience. So beyond noiseless channels. So far, all of our discussion was, we essentially had noiseless binary channel involved. So suppose we have another channel between Alice and Bob. So one very abstract way of defining channel capacity is to ask, how good is C at executing tasks? So say if C is the binary symmetric channel, one way, not the most fast way, but one way to define channel capacity is to look at all possible transmission tasks, look at the overhead you have to pay when you're using C instead of a noiseless channel, look at the ratio. This is the channel. This is the channel capacity. So how much a single utilization. Did I flip? Maybe I flipped it. Maybe it's one of the over channel capacity. But how much of an overhead do I have to pay if I'm using this noisy channel instead of a noiseless channel, and take lim sup over all tasks? That's one way to define channel capacity. For BSC, it's 1 over 1 minus h of epsilon. In the interactive setting, okay, so it is known that you can protect yourself against adversarial noise, that there are even adversarial noise, not even random noise. So even if your channel is adversarial, you can actually protect yourself against errors. But of course, in this setting, even in one way, we don't know the exact rate. So that would be too much to ask. But for a noisy channel like the binary symmetric channel, you can still just take the previous definition and stick interactive tasks here. So instead of just transmitting things, I take all possible interactive tasks and ask you, how much of an overhead do I have to pay if I'm trying to solve T over a noisy channel? And it's actually, it turns out that there is a gap. So the interactive capacity of a channel is strictly lower than its one-way capacity. And the intuition for it is, okay, so imagine the capacity is roughly something like square root. You lose something like 1 square root h of epsilon. So let me give you some intuition for this result because it's instructive. So imagine we are trying to have a conversation over a channel where each bit gets corrupt with probability epsilon. So once in a while, we'll need to do some checksum or check whether we are correct or not. How often do we do it? If we do it too frequently, we'll have to pay an overhead for doing it too frequently. If we don't do it frequently enough, every time we discover a mistake, we can just, in the one-way setting, you just correct it because I can send you a checksum and you'll correct the mistake. Here, because it's interactive, every time you make a mistake, everything that happened after the mistake is invalid. We are doing something wrong, so we have to roll back. And so if you don't check frequently enough, you'll have to roll back a lot, and everything between the last rollback is a waste. So these two concerns are optimized around h epsilon, square root h of epsilon, and that's how you get this channel capacity. But these tools are not nearly sharp enough to talk about what's the actual number. So say epsilon is 1/3. What's the interactive channel capacity? Or actually even approaching given capacity achieving code. So this only works when epsilon goes to 0. So at least we know that there is a gap, but the tools are not good enough for actually given capacity achieving codes. And there are many other open problems, especially in the multi-terminal settings and the different network topologies. OK, so that's just the open problems. And what we'll talk in the second half of the tutorial is about connections between information and communication and trying to design analogs of Huffman's coding for interactive communication, so compressing low information protocols. Thank you, and I'll take questions. Yeah.
Can you comment on the variable nature of the messages? Because that seems very important, for example, in an AND protocol.
So in the AND protocol, it's actually, why is it important?
Because zero-length messages are going on.
Well, then they're one length. There is no such thing as zero length.
No, because discretize the time.
Yeah.
Then you send your message only at a certain time.
No. The way you actually implement is you send the message. Are you raising your hand? No. And that highlights the difficulty with compression. So each of these no's is worth a lot less than 1 bit. And that's the main difficulty in this entire area is that information complexity can be realized by a protocol where each message is worth a lot less than 1 bit. So if you do something like the tricks from one-way compression from Sleepy and Wolf and all of this, you pay the 1-bit overhead that kills you. So actually a lot of it is about can you not pay this 1 bit or pay less than 1 bit. But yeah, so the encoding still use 1 bit per round. Okay, more questions? Okay, so we'll have a 10-minute break and then resume at 10:23.